Yeah, so this is my supporting talk for the Hochstetter, and so last night I talked about tectonics and erosion, coupling the two. This one is more focused on geodynamics of the Southern Alps, but I do talk about the landscape as well. So I totally changed the title that I had initially, but so yeah, the Southern Alps is told by faulting, fracturing, fluid flow, gold, and geodynamic models. So this is I think it's useful to think about where, for someone talking about their research, sort of where they came from and what their background is, because we have different stories, I guess. I actually came from chemistry and maths into geology, and I started a PhD in geology at the University of Otago. And Otago is known for tectonics and structural geology, well, it particularly was back then. And so I just put this up there. This is a sandbox model that was done actually in the lab just before so it's not something that I did, but it was just a really simple sandbox model that they used to illustrate what they were thinking about for Southern Alps collision. And so yeah, the Pacific plate modeled by pile of sand, and this ruler is the Australian plate, and they pushed it obliquely into the pile of sand to produce this model that reflects the Southern Alps and Marlborough quite well, with the steep west coast, main divide, and then the fold and thrust belt out to here, and actually even some Marlborough faults coming in where there's nothing to push against, and so the sand's kind of moving out. But really, I guess my philosophy is that modelling is the tool that I use. Some people do structural geology, some people do geophysics, but 3D modelling is kind of what I use. But a model, one, it's a simplification, and that's its power, but also its weakness. And it's only as good as what you put into it and the question you ask, and the people that you work with. And so I try and work with a whole variety of different people, geologists and geophysicists, depending on the question that's being asked. So hopefully I'll illustrate that to you through sort of the method and why that interdisciplinary work can produce some really interesting stuff. So Southern Alps, a lot of the work I've done has been informed by the Southern Alps, which are forming here along the Pacific Australian plate boundary. So the Alpine Fault is the boundary between rocks of the Australian plate and the Pacific plate in the central and southern South Island here. And we have quite oblique motion, and I'll talk a lot about that, because so it's a very three-dimensional system, which it makes it complex, but it also actually gives us a lot more information than a simple 2D system. And that motion is partitioned, so we've got about 70% taken up on the Alpine Fault, and then a wee bit on the Australian plate, but mostly here in the Pacific plate. And this is really what we're going to focus on today, sort of thinking about why the deformation that's occurring here, it looks like it does, and what's the processes and drivers involved in that deformation. And I think I really think a lot about the material properties and the boundary conditions and the deformation that we see. So I'm just going to use this block model of the South Island as an example of some of the sort of stuff I've thought about over many years. So here I've just drawn a block diagram of the South Island and looked at the different rheology, or the different rocks, and how they behave from Canterbury to Otago to Southland. In Canterbury, it's at the surface it's grey wacky. The crust, if you use geophysics, it's quite thin and it's quite strong, which was one of the reasons that the Christchurch earthquakes were really quite a strong, hard shaking for the magnitude. It's because it broke strong crust, and this is a result of the actually Mesozoic deformation, where this region was thinned in the Mesozoic. Otago, by contrast, it has schist at the surface, and it has a thick crustal section of schist, and so the material in the mid-crust in Otago is quite a bit weaker than it is in Canterbury, because here it's largely this duplex of quartzo-feldspathic material, whereas at a similar depth in Canterbury we've got a mafic crust or even down into the mantle. And then Southland is also quite thick and strong, and it's like the Western Province rocks, so granites and granodites, and so again, it's at this depth it's a lot stronger than what we see at Otago. Now, the deformation coming through this region in the Miocene was more strike slip and is now oblique deformation. So if we think of the strike slip component, so I've just drawn the section through here, and what we're looking at is the eastern part is moving relative to the western part. And so what happens if we move this, and it's driven by the mantle, so it's driven by the mantle deformation. So if we put a boundary condition of the plate velocity onto the mantle, and we have this different rheology, different materials in the mid-crust here, and it goes from strong to weak to strong, what is that? How does this velocity movement reflect up through the crust? And this is what I think should happen based on those material properties, is where you've got the strong section, the mantle, it drags everything along with it because it's all strong, and so it gets dragged along, so that the velocity that we see at the surface is similar to what it's at depth and driving it. Similarly down here, when we move to the south. But in Otago, we've got this much weaker region down here, and so we get what's called decoupling of the mantle and the crust, and so this is dragged along, but we get quite a bit of deformation taking place, and so this lags behind. There's deformation here and this lags behind, and because you've got Canterbury then Otago, we end up predicting that we might get uplift here and predicting subsidence in this region here. And that's what we see. If we go back into the geological record in the Miocene, we see that we get uplift of the Kakanui and Hawkden ranges, and they start to come up in the Miocene when it's really a strike-slip system, when it's not convergent, and we're getting uplift into this region. And we have this long-lived Lake Manuherikia in central Otago, which was just slowly, the landscape was just slowly subsiding for millions of years and producing that lake. And so that fits with what we see, what we've predicted just based on that cross-section of the different crustal materials. Once the plate boundary becomes more, we have that convergence coming in, then all of this region starts to uplift, and that convergence overtakes this pattern, and that the lake sediments and everything are uplifted, and we have the mountains cutting across that region. So I've pretty much said all of that. Yes, so yeah, difference in the pattern of deformation at the surface from Canterbury to Otago. The other thing that the weak region here means that deformation is spread out. Not only do we have it spreading out in that direction, but we have it so that the ranges spread right out across, and that's because the weak crust can't sustain as high stresses, and so the deformation gets spread out versus what we see in Canterbury. And there's also with the oblique transition, with the oblique deformation, another result of this is that we actually have this uplift that causes these ranges, but it also really focuses that uplift right up against the Alpine Fault. So it's consistent with the highest uplift in topography at around Aoraki, Mount Cook, in that transition region between that strong Canterbury and weak Otago. So this is a model that a 3D model that I've run based on that block model that we saw previously, and this is looking at the situation now. So here's that inherited boundary between strong middle crust at Canterbury, weak middle crust at Otago. We put a oblique convergence on, so this Pacific plate's moving relative to the indenture of the Australian plate here, and this model predicts similar to what I've just talked about, quite narrow high ranges in Canterbury, as we expect. We get uplift in this region, focusing around what would be the Araki Mount Cook, and deformation spreading out through the Otago crust, and these parallel ranges are starting to develop. And that's just a photo of the other thing that we see is that we have ranges that are perpendicular and parallel to the Alpine Fault in this region. So the Kirkiston Fault here, which is uplifting that, is parallel to the Alpine Fault, whereas the Waitaki Fault system is perpendicular to that. And so, and that actually, I'm not going to go into that, but that actually comes out of the model too. It makes sense mechanically that you have these two orthogonal fault structures. And mechanically what they require is that sigma 1 and sigma 2 are quite close, so that they both, and that comes out. But so this is just some geological evidence for what I've shown you of. So in the Miocene, where we had uplift on the Proto-Southern Alps and subsidence forming Lake Manuherikia, and the boundary between those two is the boundary between the Greywacke in Southland and the schist in Otago. So this is work Dave Craw put together. So in the geology, we saw this apparent contradiction where we have regional uplift at this developing plate boundary, but we also have this long-lived regional subsidence, and we're able to explain that by looking at the mechanics of the rocks that are being deformed and show how that's totally consistent, given the geology that we see. That's actually consistent with the tectonic boundary conditions that we knew were existing at the time. Oh, and once again, yeah, so that's what I just showed you. So when I'm looking at the deformation anywhere, but yeah, so in this case we're going to look at an oblique origin. What we see, the 3D stress state we see, and the strain distribution that results from that, it's really a function of these three things. It's a function of the boundary conditions, so largely the tectonic boundary conditions, but also topographic and superficial. And I talked some about that last night, but today I will show you some more of how the topographic boundary conditions can really play a role in the near surface, more from the point of view of the stress state than I talked about last night. The rheology of the deforming material, so how the rocks, how they strain in response to the imposed stresses, and which kind of follows on from that, any existing structures that we might have and what their relationship is to the plate boundary. And so I'm going to kind of use three examples from the Southern Alps to go through and illustrate those controls. So the first is looking at extensional structures within the main divide, so why and how we can get extension in the main divide region of a collisional mountain belt. And then we'll look at the role of topography in stress and permeability structure, and then finally look at some small scale models of strain partitioning along the Alpine Fault. So yeah, so in the main divide of the Southern Alps, also Taiwan and other active mountains, we see extensional veins, and these are contemporaneous with convergent structures. Their orientation varies, so that the early or the older ones tend to be sub-horizontal and the later ones tend to be sub-vertical. And they contain mineralization. Mostly that mineralization is minerals like anchorite, but there is a bit of gold. And both those indicate that the depositing fluids are hot, they've come up from depth, and the stable isotopes of these veins also indicate that the fluids that form those veins are in equilibrium with the rock. And this work is stuff I've been doing with Dave Craw for a long time, and one of the reasons that he is interested in it, because he often goes to mining conferences and often there'll be presentations on mineralized systems, and they'll say, oh yeah, it was convergent, and then there was this late extensional structure, so there was a change in the tectonic regime. It went from convergence to extension, and that's when we got mineralization. But we could see in he could see from his observations that actually we're getting extensional structures and mineralisation in these active mountains which are convergent, and the same in Taiwan. And the veins, they're contemporaneous or even cross-cutting. So he wanted to know, he could see it and he knew it was happening, but why? And what's the mechanical explanation, I guess, for why it's occurring? So yes, Southern Alps, we have hot springs along the fault or close to the fault, and then I guess the other observation is that these gold gains tended to be in the main divide. You weren't finding the mineralisation closer to the Alpine Fault, you were finding it in the main divide region. And similarly in Taiwan, I got to go into the field in Taiwan and visit this one here. They're right up in the high mountains. So there's a spatial coincidence between the main divide, the high mountains, and the gold deposits. So I did some 3D models to look at the key parameters, what is influencing, what's controlling fluid flow and gold mineralisation. The models are largely based around the Southern Alps and but also Taiwan. And they're quite simple. We tried to, again, so modelling, you try and pull out the key parameters that you want to think about, that you want to explore. So 3D block model based on the geometry of the Southern Alps, a Pacific plate that's being collided with an elastic Australian plate. So we assume that that's not really deforming. Most of the deformation's taking place in the Pacific plate. It's a two layer, so that the top layer is frictional, that's the brittle crust, and then a temperature dependent mid crust, and then it's driven by boundary conditions below that on the mantle. And so I varied the degree of obliquity in these models. So I actually did I did 2D, so orthogonal convergence. So say like what you might see in the middle of where India is ploughing into Eurasia, and then 45 degrees, which pretty much matches the Taiwanese setting, and then the Southern Alps, which are highly oblique, so that big strike slip component, but also the convergent component, which are giving you the mountains. Very simple erosion condition on this side, just to keep that western slope as it is, as we see that the erosion there basically matches the uplift. And we were looking at what's happening in this region, because this is where you predict, this is where we see gold and fluid flow. So I'm going to present the results in terms of stereo nets. Is that focused? It's not really focused for me, but and basically what I want you to get out of this is that that we can see that the stresses change with changing the convergence, and when we look at the main divide. So this is when it's orthogonal, and when it's orthogonal, it's very simple. It's basically a 2D example. So sigma 1 is horizontal, sigma 2 is horizontal, and sigma 3 is vertical. And in that situation, you don't predict any extension. It's all convergence. You don't predict any extension. But as the model becomes more oblique, the sigma 1 rotates because this vector's changing. So sigma 1 is moving from 9 to this and this. But what's more interesting is that sigma 2 and sigma 3 start to rotate. So what we see here is that these two start to rotate, and it's purely due to this change in the plate vector. And by the time we get to the New Zealand situation, the Southern Alps situation, we have areas in the main divide where they've completely flipped. And the significance of this is that means that you are predicting that there is an extensional deformation occurring within that part of the origin in the main divide region. And so you've rotated the stress tensor, and you're ending up with in this part here predicting that there should be some extension, and so it is consistent with you seeing extensional structures. You're seeing vertical pathways for that fluid to come up and deposit anchorite and gold and other things.
Phaedra, are those in your model, where are you monitoring those? Are they at the surface or at depth or variable?
Next slide. So they're here. So they are variable, and so what I've done here is this is exactly the same model, but I've just rotated it so that it's in the reference frame of the Southern Alps and Taiwan, and I just did that because I wanted to compare it with. So this is calculated sigma 1 from Carolyn Bose's paper, and then this is the model sigma 1. So the circles here are where I've measured it coming through into the main divide, and the crosses are where it's further out to the east. And so you see that the crosses and the circles, particularly in the Southern Alps example, are different. So the stress tensor has rotated between this area here where you're predicting convergence and some of this area where we're predicting extension. In Taiwan, there is a couple of crosses, but yeah, so the oblique deformation enhances this rotation and your prediction of extensional deformation in that region. So, there's another difference between Taiwan and the Southern Alps, which was quite interesting, and it goes back to the material properties. And that's that in the Southern Alps, the veins are distributed right throughout the rock package, where in Taiwan, they were really, really focused. So we were driving through the ranges and we'd see like kilometres and kilometres of sandstones where there was really no veins, and then we'd find these areas where there were just lots and lots of veins, different, they were in swarms. The younger ones were cross-cutting the older ones, so it was like they were concentrated into this region. And our explanation for this was that the two rock types were behaving differently, that because the schist had been previously deformed and dehydrated, and it had been pervasively cut up with Mesozoic veins, it was strong enough that it would break in tension anywhere really, whereas Taiwan it hasn't been previously deformed, so it's a sandstone with a weak cleavage, and in a lot of places when it was being extended it would just sort of like the phone book that some of you would have seen yesterday. So the weak layers would move and you wouldn't actually get extension, you wouldn't get fracturing, extensional fracturing. But where you did get it, once you get that extensional fracturing and you get veins formed, it actually strengthens the rock, and it means that it makes it stronger, but it also makes that it's more likely to break. And so the different rheology of these two rocks means that the details of the deformation are different, even though they're kind of experiencing the same sort of stress.
Just a quick question.
Mm-hmm.
What's the difference in age between the rocks in the Southern Alps and those in Taiwan?
Yeah, so the Southern Alps are Mesozoic, so they were formed on the edge of Gondwana and then have been through, I don't know, do we still call it the Rangitata orogeny? So that Mesozoic mountain building episode, whereas the Taiwanese rocks are largely Miocene to younger, and so they were deposited on the Chinese margin and then have been scraped off into the current collision zone. So they yes, this is their first phase of deformation, whereas Southern Alps it's the second, at least their second. Yes, yeah. So that here we have these rocks tend to be ductilely folding with restricted fracturing, but once you get fracturing, it localizes flow into those zones, and so you see these just sort of vein clusters, whereas the Southern Alps, they readily fracture right through. And so we see in Taiwan, this is the collision zone here, and this is the sediments coming in. So we see really focused veining, and it's all just really in one spot. Whereas the Southern Alps, we see veining right through, but it's only in this main divide region where we see the gold and the anchorite coming through. Whereas, so all of it's fracturing, but it's really here that extensional fracturing is focused. So the model suggests that this extensional strain and these steep fractures, they are a predictable consequence of oblique collision, and that the more oblique it is, so the more of that strike-slip component you have versus the conversions, it enhances the likelihood of the extensional strain, and it's because of the way the stress is rotated. But the details of the rock type determine how that extensional deformation is taken up, whether it is taken up just as distributed deformation as it is through most of Taiwan, or into focus veining like we see here. That's from the Karangarua. So next I want to so sort of focus in a bit more. So we're still talking about fracturing and permeability, but I'm going to focus into what we can say about permeability in actively deforming mountains, in using Manipuri Tunnel and adjacent to the Alpine Fault. There's a global permeability model which basically says that permeability decreases exponentially as you go down into the crust, and it's from observations like all over the world, and lots of them fit it, and so it's this exponential model. But observations from New Zealand, as I'll show you, observations from Nepal, Taiwan, they don't fit it, and they don't fit it, and these observations suggest that permeability in active mountains appears to be spatially variable, and in the top at least couple of kilometres, that it doesn't necessarily decrease as you go down, and it certainly doesn't decrease exponentially as you go down. And the reason I got into this was because this is work I did with Rupert Sutherland, and he had observations. So the Manipuri Tunnel goes through here, so it takes water from the end of Manipuri into Doubtful Sound. So it's this big tunnel, and there's a power station. And when they were drilling it, or when they re-drilled it, there's observations of the temperature of the rock and the fluid, which are on the next slide. And this is the observation. So we've got the temperature of the fluid and the rock, rocks red, fluids black, going through here. And there's about a kilometre of mountain on top of this tunnel. And so the kind of global model would suggest that the highest temperatures should be under there. So that they would suggest a pattern like this. But instead, what we see is almost a flat pattern, but actually the temperatures beneath the highest mountains are actually the coldest. And so that it's not a conductive profile, and it suggests that the permeability here is a lot higher, because to get what the global model would suggest, you need quite low permeabilities. And so so Rupert and I used a 3D model to try and estimate, or to try and look at what was controlling this, and what the controlling factors on the temperature were, so on the fluid flow, which led to the temperature. So I built a 3D model which included the topography of this region, and looked at the permeability, different models for the permeability structure, and tried to match with the observations. So this is a cross-section through the tunnel of the observations again. That's the topography sitting above the tunnel there. And then these are my various models. So, and we kind of went from simple to more complex. And so if it's just a uniform height, so initially we're like, well, it's just high, the permeability is just high. But but that doesn't work because we did get low values here where we expected, but the values in the valleys were way too high. This is the standard model, and that certainly didn't work as we expected. We thought about maybe it's a function of mean stress, and there was lots of other things, and I was getting quite frustrated. But I could see that the permeability had to be high in the mountains and low in the valleys. So I kind of ran this just to see how it worked. I just said, right, above sea level the permeability is high, below sea level it's low. And it matched better than I expected. And so it matched, but I was like, well, why? Why does that work? Why would the permeability be high above sea level? And because sea level you sort of think is, I mean, it's a bit random really when you're thinking about the crust. And what we came up with is that it's because of the stress state, and it's because of how close the rock is to failure. And so now did I add? Yeah, so it's not that it's sea level, but it's because the valley's basically at sea level. So it's more that the topographic stresses mean that the rock in the mountains are closer to failure. So this is taken from the model, and basically it's looking at the stress-strength ratio. So if the rock has a certain strength, which is kind of its resistance to breaking, and you impose stresses on it, and if the stresses that you impose are bigger than the strength, then you'll break it. And so we calculate what we call proximity to failure, which is the ratio. And this is, we did have tectonic boundary conditions on there, but it's really dominated by the topography. And what we found is that in the mountains, we're closer to failure than we are in the valleys. And it's because of the topographic stresses. It's because the mountain, this mountain here, it's got gravity sitting on it and it's pushing out. So it really just wants to, if it didn't have any strength at all, it would fall apart. So it's been held together by its strength, but the stresses are pushing it apart. The valleys, on the other hand, are quite strong because they've got those mountains and they're pushing it down, and so there's this compressive force on it. And when we made permeability a function of that proximity to failure, it matched really well. And so that's our model for these active mountains, is that it's and then, so this comes, if it was at failure, it would be at 1. So this is not at failure, but you had a big Fiordland earthquake to that. The bit of rock, this rock is much more likely to fracture than this rock. And so that's why we think that it's a function of, that the permeability is a function of this and then perturbed by coseismic shaking or something, and you end up with permeability within the mountains being higher than in the valleys in this region. And we took similar ideas to adjacent to the Alpine Fault. So this is the Alpine Fault coming through here. This is the Whataroa Valley, and this is the site of the two deep fault drilling project holes. So the first hole was put down in Gaunt Creek here in 2012, I think. Well, there were a couple of holes actually, so they were down to about 150 metres. They intersected the Alpine Fault and got so geothermal gradient at the base of that hole was about 60 degrees Celsius per kilometre, which is well elevated against the normal. But we know that this was a region of high heat flow. We knew that. We've known that for a long time. And then the main hole that was drilled 4 or 5 years ago, down to about 950 metres. And at the base of this hole, the geothermal gradient was something on the order of nearly 130 degrees Celsius per kilometre. So that's the drill site there, up against the side of the Whataroa Valley here. We were about a kilometre away from the Alpine Fault, which is down here. So that's a drill site. And just the topography, we're going to come back to this topography, it's really dramatic. Big valley, big sides. So we knew it was a region of high heat flow. There's lots of hot springs, lots of previous work that had been done modelling to show that we have these high uplift rates, we're bringing up hot rock, and it produces this thermal anomaly. So we're bringing hot rock up from 25 kilometres at depth along the Alpine Fault, and it's being brought up more rapidly than it can cool, so that means we have this high heat flow. And previously had been measured at Franz Joseph as well in another borehole. And also, like Dave's found evidence for boiling fluids which are quite close to the surface where the different types of... so yes, oops. And plenty, so we knew it was a region of high heat flow, high and fluid and high permeability. But what it gave us was able to give us just a more detailed look at the thermal structure in the near surface, and to estimate the permeability structure close to the Alpine Fault. So again, a series of 3D models, which I won't show you, but I'll just show you the results. So basically what we have here is that we have that hot rock coming up from depth, so that's bringing this uniform thermal anomaly up, but then we're getting this topographically driven fluid flow that's really focusing that heat into the valleys. So there's a couple of sections. So again, this here is a cut through, so looking up the valley, and we do have some topographically driven flow that's coming from the high mountains and flowing down from the high mountains and ending up against the Alpine Fault. But it's more this component that's really dominating the system and is there. So we have this big significant topographically driven flow that's taking fluid from the mountains, and it's going through these high permeability mountains and coming down and depending on where you are, hits the Alpine Fault and comes back up into the valleys. And the effect of that is that we have cold rainwater, and there's no shortage of that up here, flowing down, and it gets focused into the valleys. And so that's why, you know, at just under a kilometre depth here, we had fluids that were 130 degrees Celsius. The Alpine Fault, the Alpine Fault from the other drill hole appears to be quite a very low permeability, so these fluids get hit up there. So they collect, and in this case, unlike Manipuri Tunnel, the valleys here seem to be equally permeable as the valleys, but as the mountains. But I think there's a couple of things. One is it's so close to the Alpine Fault that I think there's just, there's just high permeability because you're so close to a really large fault. And we also have the schistosity, which gives us, so, I ran some models where I did make the permeability a function of the direction, but the high permeability direction is the same as that flow. So you have the schistosity, the foliation of the rocks, and so the permeability parallel to those planes is likely much higher than perpendicular. But that just enhances that topographic flow from those valleys, from those high peaks into the valleys. And so we end up with that concentration of heat in this region. And so quite cold. If we were to drill into the mountains, they would be quite cold because all that heat has been pulled away. So in active mountains, so we're like in Southern Alps and Taiwan, Nepal, we see that the crustal permeability is much higher than that global model, and it can be quite spatially heterogeneous. Within the mountains, greater than within the valleys, unless, as often is the case, valleys contain faults, which will increase the permeability, and that the topography is really playing an important role in this, and it's in control of where the failure occurs, where you're getting fracturing, and hence the permeability structure. And that leads on to my final section. Again, we're going to look at topography and how it's impacting stress and strain, but we're going to do that sort of in more detail, and we're going to look at it in terms of partitioning along the Alpine Fault. So the Alpine Fault, which we've kind of met already, but here it is. So this the long fault along the western side of the Southern Alps, which is the plate boundary between Pacific and Australia. It's had a lot of strike slip offset along it, you know, greater than 400 kilometres, and significant convergence as well. So the rocks that are exposed at the surface here have been buried to depths of, I don't know, 25, 30 kilometres. Now the Alpine Fault is unusual because many oblique plate boundaries like this, those two components of deformation wouldn't be taken up on the same structure. Instead, you'd get what's illustrated here. You'd get slip partitioning, which is when the converge. So you have an oblique system, and you split it into the components of strike slip and convergent. And often what happens is that the convergent component, so that the orthogonal component, is taken up on a dipping structure. So it's like a thrust, or in this example, it's a subduction thrust, and that takes up that orthogonal component. And then the strike slip component is taken up on vertical structures, and so you end up with these parallel faults. The Sumatra is a really good example of this, where you have the subduction zone offshore, and then you have a big vertical strike slip fault onshore in the mountains, and that's called strain or slip partitioning. And the Alpine Fault doesn't do that. Most of it is taken up on this one structure, except in the near surface. So right up in the top half to 1 kilometre of the fault. And this is so actually when I first started geology, Richard and Alan at Otago were doing this, and one of the first talks, Richard gave a talk describing what they'd found in their mapping, and it was one of the things that really got me hooked on geology. So it was kind of cool to now be able to run some models and kind of explain their observations. And they had said in their discussion that this partitioning that they were mapping, and the partitioning that they were mapping was that they were seeing strike slip segments and thrust segments. So instead of everything being taken up in one structure, it was being split into these two structures, but it was only happening in the near surface. And they suggested that it was associated with the ridges and valleys. And so what I've done is again, because that's what I do, built a 3D model where I've put the topography on and tried to look at what's happening and why that might be the case, why those different fault segments are associated with the topography. So this is the Whateroa again. This is the Alpine Fault coming down here. This is the Whateroa Valley, Whateroa and the Perth. So Gaunt Creek was the DFDP1, DFDP2's there. So I've built this 3D model, and I put on the tectonic boundary conditions, and I put in a predefined Alpine Fault. And I wanted to look at a couple of things. One, I wanted to look at the strength of the Alpine Fault and whether that played a role. And so one of the things about modelling is, you know, you've got to have initial conditions, and you've got your boundary conditions, and it's quite, you want to let the model develop, and so that you can look at the processes, but you don't want it to be under constrained or over constrained. And there's also, so with this, there's kind of, you know, it's all set up, and I'm not starting from where the Alpine Fault started. So I kind of ran a couple of different models so that I could, one, look at how the strength of the Alpine Fault relative to the rest of the material behaved or impacted. But then I also wanted to just let the model do what it wanted. And to do that, I only defined it to a certain depth, and then I let the material above it do what it just developed, and I varied that depth. So I varied it, so some I defined it right to the surface, and then I varied it from 500 metres down to 2 kilometres, and looked at how they develop differently in those different scenarios. And the material that I used, so the material that I used, which was to mimic the schist, it strain softens. So when it deforms, it gets softer. So you get that feedback loop that when it deforms, it gets weaker, and so it's more likely to deform. And so that's how I'm going to show you the results. I'm going to show you where the fault develops. so there's a series of different, I'll just go back. So my results are in this block here, and you can see where the Whataroa Valley is. And what I'm showing here is I'm showing the fault in blue, bedrock in red, and then the two different components of deformation. So that's strike slip and that's the convergence. And so when the fault's really weak, fault's 10 degrees here, both components are on the fault because it's weak and it's easier for them to be on the fault. Again, when it's 15, it's similar. There's a few tweaks, but it's largely similar. Once you start making this fault stronger, things change. This component, the thrusting component, still stays on that fault, even though it's not that weak. But the strike slip, it moves and it creates its own vertical structure. And it creates its own vertical structure because strike slip deformation much prefers to be on a vertical structure. And then if I strengthen my model Alpine Fault even more, the strike slip is not interested in it at all. It moves, it creates all its own structures elsewhere, and even some of the thrust material moves away. And so we end up with these two parallel strike slip structures, and this is not what we see, but it's interesting, and it's where these structures form is kind of a function of them. So this is basically forming above the base of the brittle crust. But what is interesting is this structure here. So this thrust deformation forms a structure down the Whataroa River. So it's honing in on that low point, and that's where it's forming a structure. And then these ones are where I've pinned it to a certain depth, and it can just evolve at the surface. And so basically when it's unconstrained, the strike slip will instantly go onto a vertical structure, and it will always, as soon as it can. So the dimensions here are about 500 metres because that's where it can. This one at the initial fault tip is 2,000 metres deep, and that's where the strike slip starts to form this vertical structure. And the other structures that form, we get these thrust structures forming, and they form at the base of the slope, and they're relying on that slope, and again we get structures up the Whataroa. Okay, just a couple more slides. So again, I'm throwing stereo nets at you, but so this is a map view of the stress state. And all I want you to see in this is that the red is what we would predict for a strike slip fault or nearly strike slip fault like the Alpine Fault is. So the red is what we would predict for that structure. And that's what it is mostly. But in the Whataroa Valley, so this is under the valley where you've got that big hole, it rotates, and we end up with this is sigma 2. We basically end up with sigma 2 rotating from vertical to horizontal. And the reason it's doing that is because of the hole, the topographic hole that is the Whataroa Valley. And then I can take these different faults that develop in the model and look at the kinematics. And so what we see is we get these dextral oblique thrusts, so that's kind of an oblique thrust that sort of, then we get, in this case we have a thrust, quite a pure thrust, and a parallel strike slip structure. So we've got, here we're really seeing that partitioning into thrusting and strike slip. And then the other one that's interesting is along the Whataroa Valley here. We get this structure that's parallel to the Whataroa Valley, and it's a Sinister oblique thrust. And the Whataroa is a huge valley full of sediments. You know, there's no way I can go and look for that. But one thing when we drilled when we did the drilling is, when we did the drilling, we were sitting out here just not far from the slope, and we expected to hit bedrock around about here at about 100 metres depth. and we didn't hit bedrock until 240 metres depth. So this, underneath the sediments, there's this really steep cliff, which is way steeper than anything you actually see in the topography. So one explanation for this, which fits nicely with this model, is that there's a fault there, and so that there's a fault here, and there's this side has been uplifted, or that we've just got much more focused erosion into this, and so that with the glaciers coming down, we eroded that cliff, and then it filled in, and so it was able to stay that steep.
I should point out, there might
I'm-
be another class in there. Yeah.
So, summary. Yeah. So I'm finished, yeah. So really just, again, that boundary conditions, whether they're tectonic, topographical, superficial, the rheology of the material, and existing structures in relationship to the boundary, all lead to what we actually see in the stress and the strain. Thank you.